as you may know, basically the AURORA project was really on micro nanoplastics and early life health. The AURORA project is basically running from 2021 to 2026, so it's the only project that actually goes for 5 years. So we're about at 75–80% of where we should be, so just keep that in mind when we go through that. But basically the task that we actually put ourselves on was to actually understand what is the exposure from women that are basically in a during pregnancy that actually may transfer to the placenta from the maternal to the fetal side, basically could lead to exposure to the fetus, which in itself basically could lead to early life effects. Of course, this transfer from the maternal to the fetal side does not have to actually occur to have effects on early life. If the placenta health is changed, that actually can lead also to early life effects. The reason to look at the early life effects are basically best summarized by these 3 points. One is that we actually know from all studies that we have done on particle toxicity, that we've done on chemicals, that really this is a vulnerable time period. The other aspect is that effects that actually would happen in early life have really a long-lasting effect that actually can go into adulthood. The other point is that when we look back at what we do know, if we actually look at early air pollution research, we have seen placental transfer of particles from the maternal to the fetal side, actually leading to early life effects. Similarly, we know from chemicals that are associated with plastics that these things can happen. So that was really the premise. What I'm showing you here is a kind of a summary slide of the risk assessment framework that Emily Christopher from the IOM sitting here basically put together. And this basically highlights the gaps that we actually identified within the risk assessment framework when we look at early life effects. I'm not going to go through all these different aspects, but basically they can be clustered into issues that actually surround exposure assessment, which basically was already laid out by Douglas. How do we actually quantify these exposures? Secondly, there are many research gaps that we have on the hazard assessment, may that basically be related to the particles or to chemicals bounded to particles or basically associated chemicals. And there are some issues, basically what we call paradigms and resources, and that basically is about, can we actually utilize non-animal testing? Can we actually produce reference materials that we all can use to basically make cross-reference possible? And are the existing paradigms that we have on risk assessment when we think about particles, when we think about the chemical risk assessment framework that we have, are those sufficient to actually also be applied to micro nanoplastics? Or is something else going on that actually would need us to basically think about other paradigms? When I take actually that first challenge, basically on the exposure assessment, AURORA took basically 2 approaches. One is basically a deep phenotyping approach, which basically is mostly by spectro and microscopic techniques. The other one was actually to think about how could we actually scale in samples, and that basically goes through the more fast measurements, and then you're basically in more the mass spectrometry, and I will go into more detail about that. This is really work by Florian Meyer and Laurens Zoutendijk, who basically, and Laurens Mandemakers, who really worked on the deep phenotyping, where you can see that they build up basically the spectroscopic fingerprints so that we actually understand when we look at the microscopes, what plastics are we looking at. They worked very hard and were successful in actually synthesizing different particles with different dyes, both Nile red and PDI, which we really needed to be able actually to go through that paradigm. Do they actually transfer through different barriers? And if they do, can we actually follow them and understand what their fate is? As pointed out by Douglas, one of the biggest challenges that we actually had was how do we deal with actually measuring in these biological matrices? We here basically focus both on blood and placenta material, and that are complex materials. That means that we actually had to spend a lot of time and actually figuring out what are the digestion protocols that would actually enable us to do the assessment of the micronanoplastics. Are they basically under those regimes stable, or do we actually introduce artifacts? And what are the recoveries? And this is really work that Laurens Uitendijk did. And that actually enabled us to follow basically the fate of micronanoplastics. And what I'm showing you here on the right side is a picture of a placental perfusion test where micronanoplastics are basically perfused through a placenta obtained shortly after birth. We can actually then, with these micronanoplastics that are fluorescent, see basically where do they actually transfer to, and actually do they transfer from the maternal into the paternal side. This is still ongoing work, but the first results would actually show that yes, these particles actually are taking up into the placenta, but at this time seem to be mostly accumulating on the maternal side, and the transfer to the fetal side is still something that we are looking into, but at the first experiments seem to be at least much lower, as indicated here by the yellow bars instead of the blue bars and green bars. So the other aspect that we worked on was micronanoplastic quantification, and this we call basically the fast and wide approach, and that is basically not only based on pyrolysis mass spectrometry, but actually linking 3 different mass spectrometry assays together. So that is basically pyrolysis, HRMS, which basically gives us information about the polymers and monomers, as many of the papers and evidence that we have today are based on. We coupled that to also alkaline-assisted hydrolysis, which basically gives us both also information about the polymers, but also the bound chemicals to the monomers. And we basically combine that with LC high-resolution mass spectrometry, which basically gives us the free chemicals. And so by triangulating basically these different mass spectrometry results, we hope that we actually get a fuller picture, but also able to actually minimize some of the quantification issues that actually have been seen in previous research. I'm showing you here some of the first results of actually using the different mass spectrometry here, looking at pyrolysis. This is results of the first 75 of the 800 placenta samples that we actually have measured. So what you see here is the result of those first 75. Basically, we detect plastics in all of these placentas that we actually have measured. Mostly it is PPP and EVA that are the ones that actually are the most frequently found within the placenta material. But you can see that there is a very wide scope of different plastics that actually see in the different placenta materials. This is ongoing work, which will be extended to the full 800 samples so that we actually have a better picture of these micronanoplastics in placenta material. When we go to the hazard assessment, we basically developed a tiered approach where the first tiers is basically using monolayers. The second tier is then going to more more complex systems, co-cultures and tricultures. Then tier 3, which basically goes to these placental perfusion tests where we actually perfuse obtained placentas, where we then have a whole organ. And the last tier is basically looking more at the developmental toxicity using both embryonic stem cell tests and zebrafish embryo toxicity tests. The way to do that is basically when we think about the amount of micronanoplastics, both pristine and whether that we actually would be needed to be tested, we actually need to have a logical sequence of going from simple tests to more complex tests. And that's basically what we set out. So what are the take-home messages of what we have done until now? So Hannah Dusa, who is sitting there, has done much of the tier 1 work, which has been a huge effort, where now about 19 different micronanoplastics have been tested within the tier 1. And what we observed there is basically that there are some effects when we look at cell membrane integrity and oxidative potential, but they tend to happen at really, really high concentrations. When we move forward to tier 2, and this is work that Jeske van Boksel has done most of that work, we basically looking then at less amount of micronanoplastics, mostly polystyrene and some others that are currently being tested. But what we see there is, again, there doesn't seem to be much of an estrogen-androgen effect observed. When we look at gene expression of the steroidogenetic enzymes, again, not much reaction, but what actually new results have shown is when we actually go deeper into RNA sequencing, we do observe basically toxicological pathways that are basically being perturbated, that are not reflected in the well-known markers that are normally used in these kind of tier test systems, which actually may us revisit basically what are the sensitive endpoints that we should be looking at. And that is basically ongoing work. When we look at the human placental perfusion test, and that's the results that I already showed in that slide when on the fluorescence particles, we do observe that there is basically accumulation of micronanoplastics, but the transfer to the fetal site at this moment seemed to be minimal. Again, we have to test this basically under different circumstances to see basically if that actually holds, or that there are different plastics or different setups where that transfer might be different. When we take it actually to tier 3, so this is basically looking at the embryonic stem cell tests, then we basically see that, again, there for the particles that have been tested, that there is basically a minimal effect on the cardiomyocytes. And when we look at the zebrafishes, again, there does not seem to be a lot of activity when we look at the non-lethal developmental toxicity phenotypes. So when we then go a little bit further, I wanted to touch upon the human studies. So one of the things that we set out to do was really to think, okay, how do we scale the current research from, which currently is at the moment about 100 samples, to larger sample sizes, which from an epidemiological standpoint, we really need to have solid inference of what these micronanoplastics actually could do. So we basically had two objectives with these human studies. One is to actually understand the exposures of women, and that could be basically maternal food consumption, that could be sociodemographic information or lifestyle habits. And the other one was basically then to understand if we actually quantify these micronanoplastics in cord blood and in placenta material, how does it actually then relate to placental function? How does that actually relate to early life growth and development? How does that relate to the endocrine system? How can that lead to metabolic perturbations? How does that relate to cardiovascular outcomes in early life? And how does it actually relate to immune-related diseases, thinking about asthma and allergy? And how that relates to different biomarkers. And for this, we basically devised two studies. That is basically a household study where we actually looked within homes to see what is actually the exposure to MNPs. This is work that Amanda Durkin is leading, also sitting over there. And basically did large studies within the EnvironAge birth cohort, which is a birth cohort in which the placenta materials have been stored and where the children are now at the age of 7, 8. So this actually allowed us to go back to the historical placenta material, measure the MNPs, but then actually look at the health comps at the age of 7. The same was done in the BIS cohort, which is slightly younger, where EnvironAge is from Belgium. BIS actually are Spanish children or children from Catalonia. And they basically are now at the age range of around 2. So there we look more at placental function. I'm just going to show you the results of the household study. This is where we go into the homes to actually measure the micronanoplastics in air. That was actually done by deposition measurements. And we actually look at MNPs in urine and in blood. What I'm showing you here are the results of visit 1 in about 77 homes, measuring basically deposited micro nanoplastics. And what you can see here is basically in air, PVC and PET as the most dominant plastics, what we actually measure in air. We're currently measuring the biological samples, and we have to see basically how those equate to actually see in the biological materials to actually what we have measured in these households. We're also looking at what are the sources of micro nanoplastics in the household. Do we actually understand what actually determines these air levels? May that be basically your flooring material, your textile, or your behaviors. So basically, this does not do justice to the project, neither that this conference, I think, will do justice to all the rich work that everybody has done, but we're trying to basically get the first ideas of where we are. And so I'm going back to the first picture that I've showed in the first slide of basically the rationale of AURORA going from pregnant women to basically early life effects. So when I look at exposure, it's very clear, and this might be a very obvious statement, but we know that we are exposed to micro nanoplastics. May that basically be through food or via air. This exposure is there, and we actually see that and we quantify that. We do see basically that micro nanoplastics can also be detected in placenta material. That is not that we are the first one to show that, but we actually reconfirm that it's there. With the most advanced mass spectrometry, we are now able to very reliably quantify what those levels are, but that exposure is there. What is basically the question that is on the table is basically, okay, what happens after that? Is there basically indeed transfer to the fetal site, something that we are looking into but cannot at this moment answer to what extent that actually happens? Or basically, does the micro nanoplastics lead to basically a change in placenta health, which in itself basically can actually affect early life health? And that's basically at the moment where the focus is to actually try to identify that. When I look at hazards, it's clear from the experiments that Hanna Dusse and others have done under leadership also from Marjorie van Duurse, who's leading this work package. We see basically that there are basically toxicological phenomena and effects. They occur at relatively high levels, but of course we haven't tested the large universe of all plastics, nor the complexity in which all those plastics occur. So this is what we know at the moment. Yes, it does occur at high levels. When we look basically at these more complex systems, again, the effects at this moment have been relatively minimal, but that doesn't mean that it does not occur. It does mean basically that we have to basically look further into weathering and other circumstances to see if that has different effects. The other aspect that we have noticed, and this is via our RNA sequencing, is that these endpoints that we chose from actually understanding what we normally do in toxicity and chemical toxicity, those endpoints may not be the most sensitive endpoints that actually when we look at micro nanoplastics. The RNA sequencing results actually have shown that there may be other pathways involved, and this we really have to follow up to understand what is going on. I hate to end with basically 4 question marks, but basically when we basically look at the human studies, again, we do need to show that basically these placenta exposures are there. We are now at the CUSP, and I think this name of CUSP was really well chosen for the whole cluster to actually link that information now from the 800 placenta samples to placenta health, to the early life effects. And this is basically the charge and the work that we have to do in the last year of AURORA. As this is basically not the end of AURORA, because we're still going a year, I just wanted to highlight that this is the website. Jane Monkey and team are really very well in actually putting up all the news about micro nanoplastics and early life health that comes out in the world. You can find it there. There are frequently asked questions about what is going on, but also basically with every new paper, we basically publish short videos and interviews explaining basically to the lay public what actually the takeaway message is. So I invite you to actually go to the website and keep on following us for the next 1.5 years. The last point I wanted to make is that let's not confuse the uncertainty that we still have on the human health effects to the fact that we should not basically act on plastic pollution. We know that we are using enormous amounts of natural resources, energy to produce plastics, which in its plastic production has huge human health effects. That we don't understand yet exactly what that means for early life health does not mean that we actually should start to act to minimize the exposure. So with that, I would like to leave you with that message. And I have to thank the AURORA consortium, which is a brave bunch of people that started on a project where we had not really thought about the complexity that micro-nano research really brings. And we have been, I think, amazed and surprised by the large amount of complexities. But it has been a group that actually came together to answer some of these important questions. So for that, I really want to thank the AURORA Consortium and CUSP for the very nice collaborations across these different issues that we had to solve. With that, I give it back to you, Raymond.